I'll try to keep your attention by shouting and moving around. Not really. I'm going to be talking about monads and monoids and stuff. I might not actually talk about monads. I only have 30 minutes. I just gave this talk about a couple weeks ago, and the idea was to run through as many type classes as possible and show as many examples of real-life usage and stuff like that. And the talk went okay, but the main thing was that people were like, "What? I don't even know what happened." so this time around, I'm going to try to just go slowly, take my time. Raise your hand if you get confused or you object. Well, no, don't do that if you object. Anyway, so let's just go for it. But my name is Brian. I work for LoopRecur, and we're hiring. So if you want to play with Haskell-style JavaScript all day, come and ask me. We're also going to be putting on a class in a couple weeks. Not about this, more about point-free programming. So let's do this. So the main thing here is here's a problem. We want to control access to a piece of data. And I'm just going to use a normal string with normal functions. And I say, hey, is the user an admin? Then we can do things. And this is going to be problematic. I mean, like, if I forget this, there's going to be a horrible security flaw, and everybody will know about it. So let's do some object-oriented programming. And here, I actually check inside an object. It's all encapsulated. And we make our remove dashes and valid number. And down at the bottom, I don't even have to remember. It just works, and that's awesome. Except there's a bit of a problem with this, and that's that we're normally working with a string with replace and match. And it's kind of like waking up from the Matrix when you realize this. I'm like just wrapping replace and match in my own made-up methods, and I've severely limited the API to a string. I'm just like, oh, use this instead of what you were going to use. So I think it would be better instead of like if I wanted to maybe check the length on the string. I don't have to go in there and extend the prototype and write a length method. Wouldn't it be great if you can just kind of inject a method into this object? And we can. There's a function called fmap, and it can do just that. We'll take a function, and down at the bottom, it looks a little funky, right? We're going to call it fmap. We can pass in any function, and it's going to run over our social security string. And those are just replace and split and match and whatever you're used to. With your normal data, except this time it's going to check to see if you're an admin. And this is pretty great. So what did we do? We actually just implemented our first functor. So a functor is an abstract interface with just one method, fmap. And if you look at fmap, it's going to get its function, and you have your data, and you just figure out how to apply the function to your data. And you just wrap it right back up. And the intuition is that you kind of have a box. So we had a string, we put it in a box, the social security number. And now in order to run things on our string again, we have to open up the box, run it, and close it back up. That's precisely what we do in fmap. We kind of run it inside the box on the f.number and return a new one. So this isn't really specific to strings, though, or a social security number anymore. Why don't we call it admin access? And now, bam, any data can run with any normal function, and it's going to check for your admin access. And this is way better, in my opinion, than the original Social Security thing that we made up. This just says take your normal functions and run in this special context where your normal functions and your normal data will actually work differently. Let's see here. Yeah, so we're going to make it official with this Functor wrapper. All it's doing is extending the prototype. But it looks cooler, and we can do some abstract things in there. And down at the bottom, fmap is a public function that lends itself to partial application and things like that. But what it's going to do is take its second argument and just look at the prototype on that and call the first function on that. But I'm not going to talk too much about composition and partial application or anything, but the syntax kind of works better with that. So what are the benefits? We talked about a few. One is that fmap is just an interface, and it's not even just JavaScript. It's not programming. It's language agnostic. It's programming agnostic. It's just math. So if you're familiar with fmap, there's one public method. You know what a functor is. I don't even have to write documentation, and that's pretty great. And there's another thing that you might take for granted is that we can actually just, well, actually I'm going to talk about that in a second. Let's show some more of these. So we're in observable. This is a functor too. We're going to throw in a value and just call it this.val. And then down at the bottom, you can see the box analogy again. We have a 4, and we're going to wrap it in our observable. And in order to call n plus 2 on that 4, we have to fmap the function over it. We call this lifting the function. And you kind of lift it into the context. And so the fmap here is, well, let's get the new value, see if it's changed, and fire the event with the old and new value if it has. And we're just going to wrap it right back up in the observable. So you get change notifications if it actually changes. So you can see, you get more intuition on what's going on. Like you can call things before, after, during, calling it 20 times. It's just an abstraction over function application. Here's another one. This is maybe. Maybe is a cool one. Basically says, I might have a value or I might not. It doesn't actually do anything on its own. But when you make it a functor, you kind of go with this concept of you might have something, you might not. So let's say we're getting something from the database that may or may not be there, or user input, or you're parsing something. And if we want to call replace on it, and it might not be there, what happens here is that replace is not going to blow up, even though we're put it in a null, because in fmap, we say, well, do you have a value? Actually call it, otherwise don't. And I know that's not going to work. I wanted to make it nice and simple. You'd have to check for empty strings and 0, because those are also falsy. But that's a general idea. It does work. It's just not efficient or full. Anyway, and in the bottom one, you have the letters. And it actually does have ABC, so it will run the function and return that. So you actually get the win of expressing yourself that this might not be there, and it'll just kind of silently fail. It's a cool way to just kind of ignore failures. Array is a functor in the most obvious way. It's fmap is just map, and that's not a coincidence that they're close in name. And you've just got a box of a bunch of items. We'll run the function for everything in the box and box it right back up. So I'm sure a lot of you are familiar with map. I love map. Do you guys love map? It's the best. All right, so here's something amazing. So with functors, you can actually compose them together and build up new behaviors. So we have an array of maybe observables. And I'm using the array constructor here because it looks, it just kind of gets across the point that you can use any functors. And now we're doing this fmap3. And sure enough, it'll do this function once for everything in the array if it actually is there, and it'll observe it if it runs. That's really powerful. Can you imagine a community of people all programming against functors, and you can just build up new behaviors together? I mean, like, if you just go out there and download it something, and it'll just work. Except the problem is that, nobody's really doing this yet. And that's why I'm talking to you guys about it. Also, fmap3 is totally unnecessary. People in the Ruby community and Haskell community have built, arbitrarily nested. It'll just work across anything. I just did this as an example. It's also using partial applications, so it's a little tricky there. But so how can this work? Well, there are laws you have to follow. When I first heard this, I was like, laws, what? But it's actually a good thing, because that means that anybody can just use your functor and expect to know how it works, and you can combine them. You can do all these kind of mathematical formulas based on them. And we'll see that right here. So the first one is we've got this identity function. It's just a stub function. It's just going to take a value and return it back to you. So if we fmap the identity function over your functor, it should be exactly the same as just calling the ID on your functor. That's not that hard. All it really is saying is make sure you put it back in the box afterwards, and make sure you're not dropping any other values inside your functor. So you can see here, it'll always kind of preserve the structure. You can kind of effortlessly do this. But the second law is way, way cooler. And I felt like I should show you the compose syntax here. This is how we write most of all our code at loop recur. And it's pretty weird to look at at first, but once you get used to it, it's common. You can just kind of get it. But let's just walk through it. fmap_g and fmap_f inside that compose, what actually happens is the functor will run over fmap_g, so it gets unboxed, and then g runs on your functor, and then it gets passed into fmap, which unboxes it again, and then f gets run, and it gets reboxed. And we say that's the exact same thing as opening it once and running both functions and then closing it up. So there's 2 slides here that are going to get really hardcore. Hang on with me. So right here we have admin access that we saw before. And we're going to replace and reverse it. And I know just by looking at that, I can do the line right under it, and it's the exact same thing. And it's an optimization to say, hey, I'm only going to open it once. And it'll work exactly the same way. And this is just like a mathematical formula. And that's really powerful, because you can do this programmatically. You can instantly improve and optimize things. Here's the same slide, but with a different functor. Just driving home the point that these functors are kind of hot swappable. You can just drop a different one in. And the formulas will stay exactly the same for whatever functor instance. But if we're using a list with 1,000 items, it's not going to run over it 1,000 times, close it back up, and then run over 1,000 times again. We made a huge optimization in that instance. It's just math, you guys. So here we go, functors. So we just said you can change the way you use the functions you're used to, the data you're used to, and they'll work different ways. You can build them up. And we're just dealing with mathematical ideas here, so there's no real need to, if it's not so proprietary, we can all kind of work together and build something bigger. And I really like that idea. So that was functors. Are you guys with me? I don't want to. I know I'm going really fast. All right.
Are functors not supposed to have side effects?
Well, it's JavaScript, so I wouldn't really force side effects. That's kind of up to you. You can put a side effect in a functor and try to contain them all there. And that's kind of if you understand functors, you understand like 70% of what a monad is. So that's kind of a place to contain that while your function that you've injected into it stays exactly pure. So you can have a pure program that's provable, whatever. Anyway, so yeah, good question. Thank you. So we have these page views, and they have visit lengths and clicks attached to them. And we want to know about all the page views, we want some stats on this. We want to know how long people have spent on our site, what was the longest page they stayed on, what were all the clicks across our site. So let's do that. And we can make this stats object. That's pretty cool. I've done this. How many people have made a stats object? I love that, right? Everybody loves stats. And you get like cool graphs and stuff. And you can make your longest visit and your total visit length and all the stats you want. And that's an okay way to do it, right? But I think there's a different way that you'll like a lot better. And let's look at that, but we have to take a quick detour. So there's this weird property that's hard to see, but you have a neutral element and a way to combine 2 things. So 0 and plus would work. Anything plus 0 is that thing, and plus combines 2 things. Whoa, are we all right? So in product, 1 in multiplication. That's a neutral element. Anything times 1 is that, and it combines them. Same thing with array and concat. There's something weird here. Let's make it official with a monoid. And that mempty is the neutral element, and mappend is the way to combine things. I never knew if it was mappend or mappend, if anybody wants to correct me afterwards. We have 2 instances of number here. You're actually going to have to subclass number if you want both at the same time. But I just wanted to show you can make sum or products, basically. And there's a lot more. There's empty strings with plus. That's a neutral element. Boolean and false is pretty cool. You can just or things and start with false. Or you can flip it and do and true. And you've got max and min. So there's a lot of monoids, actually plenty more than this. So what do you get if you define those 2 things? Well, you might notice that those 2 arguments are actually the 2 arguments to reduce. So now we've kind of encoded how to reduce something into the type. And if you're familiar with fold or inject or whatever, that's kind of the same thing. So it'll actually collapse this whole list of integers, starting with the neutral element, and add them together, and we'll get 15. We'll actually flatten arrays and or booleans. But the bottom 2 are pretty interesting. The tuple is a subclass of array. And it'll say, hey, instead of working like concat, let's just grab each corresponding index and combine those things. And that brings to the point that any object that is built from monoids is itself a monoid. And you can look at the bottom one there. It's just an object literal. And it's built entirely of monoids, so it's a monoid. And we can have D as a key. And that's another object built from monoids. And It can just have these giant structures. And once you get down to primitives, as we've seen, just about every primitive is a monoid in multiple ways. So just about everything's a monoid, right? So let's revisit our problem. We can make a monoid instance for page view. And this is a little tricky to look at first. But if you look at the top, it's got the neutral elements, right? 0 in the empty array. And then in mappend, we're going to take page view 1, page view 2, and just mconcat them together. And they know how to combine themselves, so they will. And what we get is the total visit length across the site and every click across the site. We do this a different way just by changing max and tuple. Those are the only two things that changed. And what we said is, hey, use this type and use this type. And now it kind of mashes together the clicks. I just did that for fun. But the max, actually, that's the longest page view. It'll always keep the maximum one as you combine them arbitrarily. So we tell them how to do, hey, combine this and this. And we've defined how to combine them. And now we can just give it as many as we want. This is the easiest way, though. We didn't actually have to do anything, because we knew that any object built entirely of monoids is a monoid. So we can just call mconcat and we're done. And I think that's a lot better than this one. I hope you guys do too. So let's look at this other instance of monoid function. And a function's a monoid if its return value is a monoid. So in mappend, the way to combine two functions together would be to return a function that runs both functions, and they can be run at the same time and combine the results. So here's a toy example, and you can do really powerful stuff with this. But starts with A and ends with Y are just two functions that return a Boolean. And so in our filter, if our first argument into filter is a function that returns a Boolean and the second is an array, what we'll do here is mconcat, which built up a new function that for every element, it runs on both and then combines the result with OR. So it either starts with A or ends with Y. And we can do that. We can add more and more in there. It's not just two. And we can do crazy wild things. It's just going to drop the argument to all the functions. It can do that concurrently and combine the results. Let's speak about that for a second. Here's a law. And the top two just say MMT is in fact neutral. It's not going to cause any problems. But the bottom one is associativity. It says if you've got an mappend inside an mappend, it doesn't matter if you combine X and Y or Y and Z first. And what that means is we can just chop our list into a bunch of different partitions and combine them all at once. And that's a really powerful thing too. It's like MapReduce, right? So that's monoids. Yay. So it's going to give you a way to accumulate results. And you don't have to think of it just in terms of statistics and stuff like that. I mean, if you have accounts, let's say some jerks on your site like make an account after account, and then he's like, hey, I have too many accounts, I want to combine them. Well, you just define how to combine 1 and 2. Maybe just keep all their friends or their account balance or something, and then you can combine as many as you want. There's also something that I don't know that much about, so I shouldn't talk that much about. But a buddy of mine came up afterwards last talk and said that you can form a semi-ring by combining a monoid with another monoid. And there's a couple extra conditions on top of that. But he said he was solving the wildest problems because these people have algorithms out there that you can just use because they're just for monoids, and you can just change the monoid instance you're using. So you can imagine that you have like every route possible to this one destination, and you just use the min monoid, and it'll tell you the fastest way to that destination. So really powerful stuff that you don't have to write because it's coming from deeper things with formulas and junk. Let's see. I have 9 minutes, so I don't know if I'm going to be able to explain monads in 9 minutes. I can do a quick look at them. So let me just scratch the surface here, and maybe I'll spark some interest in you guys. I cut out applicative functors, and they're my favorite, and it hurts. But let's see. Let's start here. So mresult and mbind, it's a lot like a functor. And if you think about it, mbind it looked a lot like our functor instance from before. It says if you have a value, actually run the function on the value. This is that maybe thing, right? If it doesn't have something, it shouldn't run the function. And mResult gives us a way to wrap it back up. We don't wrap it back up by ourselves. So in Call Me Maybe here, it looks a lot like fmap, except our argument is not the function first, but it's our monadic value, our maybe with the params ID, which might be there and might not be there. And the reason for this, there's these two distinct differences. We flipped the argument in the function in this mbind, which works just like fmap. And then we've given a way to rewrap it by yourself. And the reason they do that is because you can nest these things and depend on previous values in a pure functional way. And this says, hey, if we have an ID, pass it to that function. I know, this is hideous, by the way. I'm still looking on some better syntax. I've done this. But let's look at this for a second. So we have, get the user, and if you don't get anything back, just stop. It'll cut the whole rest of the computation off. But if it does get it, it'll pass it in, and it'll just keep going like that. They kind of nest. These are like nested null checks. And this is totally type generic. So you can see that if this was a list instance, it would be nested maps inside of maps, and so on and so forth. You can do really crazy stuff with it. I've been working on this experimental syntax. That's kind of crazy. It's just ported from Haskell, but it'll just kind of turn your function into a string and write a new function after it converts it to this looking thing. But I just wanted you guys to get a quick idea of what a monad is, now that you kind of know what a functor is and it's fresh. And it's just kind of a way to, now that you all know what a functor is. But it's a kind of a way to combine things and nest them. But you get a lot of benefits. You can actually implement fmap with a monad. Let's see if I can find that. Yeah, there you go. Down at the bottom, let's say we have fmap.name on our users. It'll actually make the DB call come back, and we're just grabbing the name. It's like you can think of the DB call itself as a box. And we're going to open up the box, grab the user, and run name on it, and close it back up. Well, we can actually implement that monadically, so it's more powerful. But it is, in fact, a monad is a functor. Anyway, I'm on a tangent. I shouldn't be talking about this stuff. Let's just do a summary here. Let's see. So if we were all to kind of work together and build up this stuff from math, then there's only a handful of functions that you really need to learn and concepts that you need to learn. And then you just work with your normal types and your normal data. And we can actually compose our stuff with the rest of the community stuff and kind of push forward. Can you imagine if you're doing a real-time web app and you wanted to talk to the server and the client, but everything was pure and nothing was immutable? I mean, there's some really powerful stuff there. You could also talk the same language on Ruby as you are in your JavaScript. So, you're still working with functors there. There's no need to make your own object in a lot of instances, and you can build them up and compose them, maybe serialize them in different ways that we never thought of. So I just wanted to encourage you to maybe look at the Haskell community, because they're doing this today. People are rewriting their libraries to say, oh, well, this is just an applicative functor. Oh, this is just a functor. And they're not doing like, read my documentation. This is my crazy idea. And I think that's all I really have to say. So we got a couple minutes for questions. I'm not trying to sell tickets to my talk or class. All right, here we go. So that's my talk. Thank you. That was fast again, I think. Are you guys all right? Did I hurt anybody?
I have a question. In the beginning, you made a statement about functors are like something else. You said, I'm not quite remember what that was.
Oh, like a trait, like in aspect-oriented programming, you can combine them, perhaps?
Yeah, I think so. Do you remember what you said exactly, or you went real fast?
I probably did. Roll back the tape.
You can put these online?
Yeah, they're actually already on SlideShare, and it's missing a couple of slides because I revised it. I was doing this magical Safari tour. It was weird. What's up?
So why are you choosing to do this in JavaScript instead of Haskell or Scala or?
It's a great question. We love Haskell, but we can't sell programs in it. And
Okay.
yeah. But honestly, like I started doing this years back to learn Haskell. I thought, hey, why don't I just port, if you just go grab O'Steele's functional JavaScript, you can write Haskell code with JavaScript. I've got a fork on my GitHub that just makes it actually all auto-curry, so you don't have to do that yourself. And Woo.js actually is, I just stole the auto-curry from it. I don't use anything else, but it's awesome. What's up?
Yeah, with your nested closures,
Yes.
callbacks, you might want to talk to the guy who did the previous presentation on promises.
Yeah, I know, seriously. I read a lot about monads with promises. Jay Coughlin has some really good work. We're going to connect afterwards and drink a lot and talk a lot, so it'll be good.
We work great together.
Yeah, oh, there you are.
Great tastes that go great together.
Yeah, yeah. No, I don't recommend that nested mbind stuff at all. I think it's a really good thing to understand, and then maybe we can work on a better syntax, because the jQuery as a monad thing is really cool, but it doesn't nest as well as it could, I think. You don't really have the ability to do these nested lambdas. What's up?
Have you looked at like any of the other compiled to JavaScript languages, like Roy or Fay or anything?
I have.
More functional along these lines?
I do like those, and I would like to get into them more, but I like vanilla JavaScript. You have first-class functions, you can compose them. We're doing Node, Titanium, and browser, and I don't have to do any other work than just writing the same composition strings. So it's pretty cool to be able to jump. I do have to change the.
You're kind of starting to get into it, like with that do monad function that's rewriting.
Yeah, it's like runtime processing. Yeah, that was more of an experiment than anything else. I think monoids and functors and applicatives are definitely useful. Monads, don't know yet, but it could be. So yeah, and I think I got a couple more minutes. Anybody else want to? All right, cool. Well, thank you guys so much.